Hello, my name is Rahid Isam Al Huslan, and this is my presentation for Project 1 image compression using LZW coding. So, what is a compressed file? A compressed file is a file that has been reduced in size using compression software. The process of compressing a file is to reduce its size, making it easier to store and transfer over the internet or other electronic media. The compression software uses various algorithms to eliminate redundant or unnecessary data in the file, which result in smaller file size. And there are several types of compressed file formats, including the most famous one, zip, and RAR and gzip, among others. These formats have different compression algorithms and features, but all are designed to reduce the size of files. Compressed files can be created and decompressed using software specifically designed for that purpose, and most operating systems have built-in support for common compressed file formats. So, why data compression is important? So, data compression is important for several reasons. First one is to reduce the storage space. Compressing data reduce the amount of storage space required to store data, and this is particularly important when dealing with large files such as multimedia files, which can take a lot of space. Second reason is faster data transfer. The compressed data can be transferred over the internet or other electronic media much faster than uncompressed data, as there is less data to transfer. Third reason is to saving the bandwidth. Compressed data require less bandwidth to transmit, which is important for applications such as streaming videos and audios where there are limited bandwidth available. Fourth reason is which is important for which is why is it important is for saving the money. Compressing data can save money on storage costs and reduce the amount of bandwidth required for the file transfer, which can result into saving money. And this is especially important for businesses that deal with large amount of data. The types of compressions. There are two main types of data compression, lossless and lossy. So the lossless compression is a method of data compression that allow the original data to be perfectly reconstructed from the compressed data. That this means that no information is lost during the compression process. And lossless compression is typically used for text files, program files, and other types of data where it is important to preserve the original content of the file. Example of lossless compression algorithms include zip and gzip and LZW, which I'm gonna speak about today. The second type is the lossy compression. The lossy compression is a method of data compression that is sacrifice some of the original data to achieve higher level of compression. So in other words, it means that some of the data are going to be lost in the compression process, and it's typically used for multimedia files such as images, audios, and videos, where it's acceptable to lose some quality in exchange for smaller file sizes. Example of lossy compression algorithm include GBG, MB3, and MPEG. LZW is a lossless data compression. As I said, so here we have the lossless compression file types, some of the types, and here the lossy compression file types, which is JPG and GPG. Here we have a photo shows the difference. We can see here that this is perfectly compressed and decompressed. On the other hand, here we see that it's kind of lost some of its quality. In here, I'm gonna start speaking about the LZW compression algorithm and how it works. So it works by replacing repeated sequences of data with a code that represent the sequence, and the algorithm build a dictionary of code as it's compressed the data and uses this dictionary to compress the data back to its original form. Here we can see some example. Here we have the dictionary, and then at each step we're gonna hold on to the character that we have in the dictionary and append it to the next character in the giving string. And if it's not in the dictionary, we're gonna add it and output. Definition of the project. Here I have some bullet points of the definition of this project, which is an LZW encoding based compression, has 6 levels. Compression and decompression are separate and can be colored or gray, and can be different or non-different images. The levels of the project, here we have the 6 levels. So in here I'm gonna speak about level 1. In level 1, we implement a basic LZW compression and decompression algorithm using the Tkinter library for the GUI interaction. And the LZW algorithm here works by creating a dictionary of string from the input data. In here, we initialize the first 256 ASCII characters, then we encode the data in we encoding the data using the index values of the strings in the dictionary, and the result list is then saved to a new file, which is the same file name and the original file name, and has also a compressed word attached to it. And then we add the extension. The code length and compression ratio are also calculated and displayed in a pop-up message. Then last step, the compressed data will be decoded by rebuilding the dictionary, and we're using the index values to look up the original strings. The results is then saved to a new file with the same name as the compressed file, but we add decompressed added to the file name. And the original and restored text then compared. As we see here, the original and restored text are identical. We display this message to display if it's identical or different. For level 2, it's basically similar to level 1. We implement the LZW algorithm for compression and decompression, but in this level, instead of text, we are using images as input. We convert the input image to grayscale, black and white, and compress it using LZW, and then we calculate the entropy and average code length and compressed file size and compression ratio of the compressed images. Additionally, we save the decompressed image as a PNG file. Here we see the photo that we compressed, and here the decompressed photo, which is showed as a grayscale level, and here we have the pop-up that shows the results of our compression. For level 2, this level deals with the compression and decompression of the images using the LZW algorithm, same as the past levels. And the algorithm in here works by first converting the image to grayscale, then calculating the differences between the adjusting pixels. These differences are then compressed using the LZW algorithm and saved to a file. And then the compressed file then can be decompressed to retrieve the original image. Here we have the information, and here we can see the original image and the decompressed image side by side, showing in the interface. For level 4, in this level, I have some function called compress image. This allows the user to select an image file, same as the last level. But in here, I convert to the RGB component into NumPy array. Then I compress this NumPy arrays using LZW. Then I concatenate the compressed data for each channel with appropriate delimiters, and save the compressed data to a file. The function also calculate and display entropy, average code length, compressed file size, and compression ratio. For the decompressed, we select that data file and load the compressed data and dictionaries from the file, and decompress each RGB component using LZW, and reshapes decompressed data into a 2D array, and merge RGB component into a single image using PIL, the PIL library, and we save the restored image to file. Here we can see the compressed and the decompressed image. For level 5, in this level, we have the graphical user interface, which is run the LZW image compression algorithm, and we scan the differences image, and I achieve this by splitting the image into color channels, compute the differences between adjusting pixels, and compress the differences using LZW compression. The compressed data is then saved along with the differences shapes, and then the decompression algorithm restore the compressed image by decompressing the differences data and adding it to the original image. I have in this level a compress function, and this function opens an image file and convert it into an NumPy array using the PIL library, and the color channels of the image are splitted into separate arrays for red, green, and blue, and the differences between adjusting pixels in each channel are computing using the NumPy.different function, and this result into a 2D array. The differences are then flattened into just one 1D array using a flatten method. Then this LZW compression algorithm is applied to the is applying the flattened differences arrays for each color channel, and replace repeated occurrences of a string with a dictionary reference to that string. And this technique reduce the size of data by reducing the number of bits required to represent the data, and compressed data then be saved using the save is compressed along with the shape of difference array. My decompress function compare the image data. The compressed data is also loaded from the saved file using numpy.load function, and the differences shapes are loaded to construct the 2D differences array for each color channel, and the LZW compression algorithm applied to each channel compressed differences data. Then the compressed differences array summed with the corresponding color channel of the original image to restore the compressed image. And then I've gathered all these levels in a GUI with a drop down that shows all the levels. When I click the level 1 or level 2 or level 3, it calls this level and open it in a separate Canva. Thank you so much for listening.